Welcome back. In this video, we can discuss about how to find the minimal cover of a functional dependency set. This minimal cover is also known as the canonical cover or the irreducible set. So first consider the definition. A minimal cover of a set of functional dependencies F is a minimal set of functional dependencies F min that is equivalent to F. That means you are provided with a set of functional dependencies. We can call it as F now. And take some dependencies from this F. And that subset is called as F min. If this F min can perform all the activities equivalent to this F, then this F min form the minimal cover of F. Once more, a set of dependencies F min that is derived from this F, right? Some dependencies from this set F is taken to form a new set, that is this F min, and this F min can have the same capability of this F. Then we can call this F min as the minimal cover of F. Okay, there can be many such minimal covers for a set of functional dependencies F. We can find out more than one number of minimal covers for a given functional dependency set. So we can consider next about the steps to find the minimal cover of a functional dependency set. Okay, the first step is ensure that the RHS part of all the functional dependencies should contain single attribute. Means you are provided with set of dependencies. We can call that set as F. And suppose that F contain a particular dependency like this. A implies BC. The right hand side contains more than one attribute here. So with the help of our decomposition rule, we can rewrite this A implies BC as A implies B comma A implies C. So this is the first thing. First step, make sure that the right hand side contain only single attribute. Second step, eliminate redundant functional dependencies if any. Eliminate redundant functional dependencies if any. Suppose the set contains the functional dependency set F contains dependency like this: AB implies C and C implies A. From this it is clear that with the help of this AB implies C, we can find out the value of A attribute, B attribute as well as C attribute. So here this C implies A is a redundant dependency, right? We don't want this C implies A here because using this AB implies C, we can identify both AB and C. Right? So this C implies A form a redundant dependency here. So we can remove such redundant dependency and make a new set, that is AB implies C. So this form the minimal set. The second step is eliminate redundant functional dependencies if any. And third and the final step is remove redundant attribute on LHS. Consider each and every dependency is present in the set and check the LHS part. If there exists any redundant attribute in the LHS part of the dependencies, then remove it. For what? For that, what we want to do? Consider a dependency like this. AB implies C. Here, the LHS part contains more than one attribute. Okay, in order to check whether this A and B are redundant or not, what we want to do? Find the closure of AB first. AB together find the closure. Then find the closure of A alone. Using the set of dependency provided, find AB closure first, then find the closure of A alone. That means here we have used A only. B is eliminated. And this AB closure become equal to this A closure. From this it is clear that without using the B attribute value, we can identify all the attribute values that this AB can. right? AB closure become equal to A closure. This indicates that B is redundant here, because without using the B value, A alone can perform all the activities that this AB can perform. So from this it is clear that B is redundant. So in that case we can reduce this AB implies C as A implies C. Similarly, check for the redundancy of A if we need it. Like this, if AB closure equal to B closure, from this it is clear that without using the A attribute value, B alone can derive the values of A and B. B alone can perform all the activities that this AB can. So from this it is clear that A is redundant here. So in such situation we can rewrite this AB implies C as B implies C. So these are the three steps in order to derive a minimal cover for a given functional dependency set. So consider certain examples. So first, this is the given dependency F. A implies BC, B implies C, AB implies D. So after the first step, what was our first step? Make sure that the RHS part contains single attribute only. So in the first dependency A implies BC, here we have two attributes. So with the help of this decomposition rule, we can rewrite this as A implies B, A implies C. Then B implies C, AB implies D. So this is the output of first step. All the dependency contains single attribute in the RHS side. So using this output of step 1, use this as the input of step 2. Okay, so we can start the next step. Here we can use the output of first step as the input. So the second step is check whether these dependencies are redundant or not. So start with the first dependency A implies B. Check this A implies B is redundant or not. For that, find the A closure. Using these set of dependency, find the A closure. Okay. So after finding the closure, once more we need to calculate the closure, or we need to find out the A closure. But here we need to avoid this A implies B from the set. So without this A implies B, the F become A implies C, comma B implies C, comma AB implies D. So using this set of dependency, again calculate this A closure. So the A closure here is A, comma C. Now check whether this A closure and this closure are equal or not. Here it is not equal. That means without this A implies B, the F set can't perform all the activities. So A implies B is irreducible. This is not redundant here. Why? Because without this A implies B, the functional dependency set can this functional dependency set can't perform all the activities, right? That is why the closure become different here. So from this difference we can conclude that A implies B is irreducible, or it is not redundant. So go for the next dependency. Check A implies C is redundant or not. So the same rule. First find the closure of A, because here the LHS part is A. So find the closure of A. The same A, B, C, D. So after that, without this A implies C, again find the A closure. Without A implies C, the F become A implies B, B implies C, AB implies D. Right? So again the A closure become A, B, C, D. That means from this set A closure is A. If we know A, we get B. If we know B, we get C. With the help of A and B, we can derive D. So from this it is clear that with and without A implies C, A closure is the same. After avoiding this A implies C from the set F, A closure become exactly equal to this. That means A implies C is redundant here. The presence of this or the absence of this A implies C. It does not make any change here. The absence of this A implies C does not make any change here. So from this it is clear that A implies C is reducible or A implies C is a redundant dependency here. So in that case, immediately remove A implies C from the set F. Right? If such a reducible dependency is found out, immediately remove from the set F. That is the next step. So after that, this F become A implies B, B implies C, A, B implies D. A implies C remove from this set, because in the previous step we have concluded that the A implies C is redundant. So immediately remove from the set. So this is the new functional dependency set F without A implies C. Okay, so after that again continue with B implies C. Check the redundancy of this B implies C. So using this new set, find the B closure. That is B and C in the B closure. After that, without B implies C, again find the B closure. Without B implies C, the B closure contain B only. This closure and this closure is not equal here. That means this B implies C is not redundant or it is irreducible. We can't eliminate B implies C from the set. Okay, so continue with next AB implies D. Check this AB implies D is redundant or not. For that, first find the AB closure using this set. AB closure is AB directly added in the closure set. Then we can derive C and AB can together derive D. So after that, without AB implies D, find out the AB closure again. Without AB implies D, this F become A implies B and B implies C. Okay, the AB closure become A, B, C. A, B and B can derive C. Here again, this AB closure are not equal. So from this it is clear that this AB implies D is not redundant or it is not irreducible. Sorry, it is not reducible. That is irreducible. So after the second step, now we have completed or considered all the dependencies, or we have checked the redundancy of all the dependencies present in set F and eliminate A implies C here. Okay, so the final output of second step is what? A implies B, B implies C, A, B implies D. So using this output of second step, we can start third step. Using this as the input, we can start third step. Okay, so what was that third step? Check the LHS part contains redundancy. Okay, so for that check, in any of this dependency contains more than one attribute in the LHS here. In the third case, it is clear that the LHS part contain more than one attribute. Here we have two attributes. So check whether this A and B are redundant or not. Okay, so for that what we want to do, first find the closure of AB. Then find the closure of A alone. Then find the closure of B alone. Then check whether they are equal or not. Okay, so the AB closure is A, B, we can derive C and B, AB can together derive D. Okay, after that find A closure. In order to check whether B is redundant or not, find the closure of A alone. The A closure is A directly added in the closure set. A can derive B, B can derive C, then AB can derive D. From this it is clear that this A can derive all the attribute, or A can perform the activities which is similar to the activity of AB. That is why the closure set become equal here. That means A closure equal to AB closure means B is redundant here. AB closure equal to A closure means B is redundant. Okay, now we can check the closure of B also. B closure means A is not present here. So this is actually for checking the redundancy of attribute A. So the B closure is, B is directly added here, B can derive C. The BC closure not equal to AB closure. So from this it is clear that without A, B alone can't derive all the attributes that this AB can. That means B closure not equal to AB closure. So this from this B closure not equal to AB closure, it is clear that A is not redundant. But A closure become equal to AB closure. Here B is absent. A closure become equal to AB closure. So it is clear that B is redundant. So we can rewrite this AB implies D now as what? A implies D. We can remove B here. B from here because B is actually redundant. So the final minimal cover of the given F is A implies B, B implies C and A implies D. So this is the final answer for the given dependency set F. Okay, consider one more example. The set of dependencies A implies B, A, B, C, D implies E, E, F implies G, H, A, C, D, F implies E, G. Right? So the first step, make sure that the RHS contains single attribute only. So here it contains single, here it contains single attribute, but here and here contains more than one attribute. So we can rewrite this as A implies B, A, B, C, D implies E, E, F implies G, E, F implies H. Apply the decomposition rule here. And here also apply the decomposition rule and separate E and G. Okay, so use this as the input to the second step. And check the redundancy of each and every dependencies present in this set. So start with the A implies B. For that, what we want to check? First find the closure of A. A implies B is redundant or not. We want to check this. So find the closure of A from this set. So which is actually A comma B. A can identify A and B only. Okay. After that, avoid this A implies B from this set and using the remaining dependency, find out the closure of A again. So avoiding this A implies B, the set like this. The set become like this. So from this, the A closure is A only. That means from this set it is clear that A alone can derive the value of any other attribute. So A closure contain A only. These two closure are not equal here. So from this it is clear that A implies B is irreducible or not redundant. So we can't avoid such dependency A implies B from here. So using the same set, check the redundancy of second dependency. A, B, C, D implies E. Check the redundancy of that dependency. So find the closure of A, B, C, D first. This is the dependency. This is the closure of A, B, C, D. A, B, C, D can derive A, B, C, D directly and E also. A, B, C, D can derive A, B, C, D using reflexive principle, and using this we can identify the value of E also. And without this A, B, C, D, E from this set, the remaining dependencies are A implies B, E, F implies G, E, F implies H, A, C, D, F implies E, A, C, D, F implies G. In this set, find out the closure of A, B, C, D again. Now this A, B, C, D can derive A, B, C, D, and using this we can't identify the value of any other attribute. So this is the final closure. These two closures are not equal. So from this it is clear that this A, B, C, D implies E is irreducible. Okay, so check the dependency of next. That is E, F implies G. So first find the closure of E, F. This is E, F, G, H. EF can derive E value, F value using the reflexive property and the G value also. And also this H value. And after eliminating EF implies G from the set using the remaining dependency, here we haven't that EF implies G. Okay, so after avoiding this EF implies G, try to calculate the or try to find out EF closure again. The EF closure is like this. EF can derive E value, F value and H value. So from this it is clear that these two closures are not equal. So the absence of this EF implies G. It will not generate a closure set equivalent to this one. Okay, so from this it is clear that EF implies G is not redundant or irreducible. So go for the next dependency. EF implies H. Check if EF implies H is redundant or not. Right, the EF closure without eliminating anything, EF closure is this. EF can derive E value, F value with the help of reflexive property, then G and H using these two dependencies. Without EF implies H, in the set, while removing this EF implies H, find out the EF closure again. So it is E, F, G. This is not equal. So we can conclude that EF implies H is not redundant or it is irreducible. So go for the next dependency checking. So here it is, ACDF implies E is redundant or not. So find the closure ACDF first. ACDF means it can derive value of ACDF directly with the help of reflexive property. Then this ACDF can derive E and G, and EF can E and G value. Then EF can derive this H value. Then A can derive the B value. Okay, so after removing this ACDF implies E from the set, using the remaining dependency, again calculate the closure, ACDF closure. The closure is like this, ACDF GBEH. ACDF directly from this, and A can derive B also. ACDF can derive G. This EF can derive H. Okay, that means it is clear that the closure set are equal. Without the dependency ACDF implies E in the set, the ACDF closure can derive the attribute set which is equal to this particular set. That means ACDF implies E is a reducible dependency or it is a redundant dependency here. Okay, so it is a redundant dependency here. So if such dependency is found out, what we want to do next? Immediately remove that dependency from the given functional dependency set. After removing this reducible dependency ACDF implies E from the given set, now the set become like this. A implies B, ABCD implies E, EF implies G, EF implies H and ACDF implies G. So here in the previous step it is clear, we have concluded that this one is redundant. So eliminate this one immediately from the set. Now the set become like this. So using this set check ACDF implies G is redundant or not. So find ACDF closure first. Here it is the closure ACDF. Then it can derive G value and G value using this, and thus EF can derive G and H value A can derive B. Okay, so without this ACDF implies G, the set become A implies B, ABCD implies E, EF implies G, EF implies H. So using this the ACDF closure become like this. So it is clear that the closure set are equal. So absence of this ACDF implies G here, it does not affect the closure. That means this is actually a redundant dependency, or it is a reducible dependency. So immediately remove that ACDF implies G from the set. So at the end of the second step, the dependency set become A implies B, A, B, C, D implies E, EF implies G, EF implies H. So together we can write it as EF implies GH. Okay. So using this dependency set, we can start our third step. So this is the step, or this is the functional dependency step after step 2. So using this, we can start step 3. In step 3, we need to check whether redundant attribute present in the LHS part. So in the second dependency and the third dependency, here we have more than one attribute. So check whether redundant attribute exists there or not. So start with this ABCD implies D. So find the ABCD closure first. ABCD closure is ABCD, then it can derive E. No more attribute. So this is the closure of ABCD. After that, find the closure of these ABC closure in order to check whether this D is redundant or not. So this ABC closure is ABC alone. That means while removing this D, this ABC attribute combination can't derive all the attribute values that this ABCD can perform or ABCD can derive. So from this it is clear that D is not a redundant attribute. So we can eliminate D from this LHS part. So continue with next ABD closure. ABD closure means C is absent here. So now checking whether this C is redundant or not. So this ABD closure can derive using this set. ABD closure is ABD only, which is not equal to this ABCD closure. So C is not a redundant. Okay. So absence of this C, the derived closure is not equivalent to this ABCD closure. It means C is not a redundant attribute. Okay. So we can't eliminate C from the LHS part. Now here it is the ACD closure. ACD closure means B is absent here. So ACD closure can derive all the attribute which is present in this ABCD closure. That means absence of B, it does not affect the property of this ABCD, or it can perform all the activities that this ABCD can without including B attribute here. Okay, so it is clear that B is redundant here. Why? Because the ACD closure become equal to ABCD closure. This B is absent here and the closure set are equal here. That means B is redundant here. That is why this ACD alone can derive the same closure set of this ABCD. So from this it is clear that B is redundant. Again check this BCD closure. This BCD closure is BCD alone, which is not equal to this ABCD closure. So that means A is not redundant. Okay. So from this, B is the only one attribute which is redundant here. So we can rewrite this as ABCD implies E as ACD implies E. The redundant attribute B in the LHS part is removed. Now go for the next dependency. EF implies GH. Okay. So EF closure from this set is EF GH. Okay. EF GH. E closure alone is E and F closure alone is F, which is not equivalent to this EF closure. So E is not redundant and F is not redundant. Okay. So the final minimal cover for the given attribute set is, minimal cover for the given functional dependency set is A implies B, ABCD implies E is reduced to ACD implies E, EF implies GH. So this is the minimal cover for the given dependency set. Okay, so these are the 3 steps for deriving the minimal cover for a functional dependency set. Okay, thank you.